Hello chemists and welcome back to another episode of Bales Chemistry. Today we are going to finish up the electrochemical cells topic. That is 1.11 on the AQA A Level specification, and it does appear on paper 1 of your A Level final exams. We're going to look at more electrochemical cells today. Couldn't think of a catchier title, but in this episode we're going to look at what happens when we're talking about non-metals in electrochemical series and how we measure their standard electrode potentials, what happens when we change the reaction conditions, and to finish up, how we can predict which direction a redox reaction might go from electrochemical cells. In the last episode, we looked at the electrochemical series. We looked at the metals that were most reactive being at the top of the table and the metals which were least reactive being at the bottom. Now, you can put non-metals on the electrochemical series. Now, these ones are always going to be positive values because they're going to be better at accepting electrons than they are at donating them. But again, the same principle applies. So the ones at the bottom are more easily reduced. They are better oxidizing agents and they are the most reactive nonmetals. So by this sort of logic, the ones higher up the table will be the least reactive nonmetals. Measuring the electrode potential of a nonmetal is a little bit more complicated. There's no metal which will conduct the electrons into the circuit. So for this, we use a platinum electrode similar to when we use a standard hydrogen electrode. Also, with nonmetals which are gases, we use a similar setup where we bubble a gas over a solution of its ions. In some half cells, like with iron 3+ becoming iron 2+, both the reduced and the oxidized form are both in the same phase. This makes it a little bit more complicated to draw out the electrochemical cell. We place a comma between the Fe3+ ion and the Fe2+ ion to show that they're both separate ions, but they are there in the same phase. We can also change the reaction conditions of the half cells, and this has an impact on the overall electrochemical cell. Half equations are equilibriums, so they follow Le Chatelier's principle. If you change the reaction conditions, you'll ultimately change the cell EMF. If we look at this example of a zinc cell with a copper cell, and we just focus on the zinc for a minute, if we increase the amount of zinc, we'll increase the number of electrons, because as we increase the amount of zinc, Le Chatelier's principle will shift to the right and produce more electrons. This will of course increase the cell EMF because we'll now be pushing more electrons into the circuit and pushing more electrons over onto the copper side. We can use values from the electrochemical series to predict the direction of a redox reaction. If we look at this example here where we've got copper and zinc in solution, we've got two possible reactions that could take place. The first one with the copper solid becoming the copper ions, and the second one where the zinc solid becomes zinc ions. So we'll start off by looking at those values up on the electrochemical series. Now we can see here that zinc is the more negative of the values. The more negative value will be the oxidized one. So we can switch that round and we can write that out now as zinc solid becoming zinc ions plus the electrons. We'll keep the copper the same because copper's reaction will stay as the reduced form. And then we can combine those two half equations together to get our final equation where the copper 2+ ions reacting with the zinc solid to form zinc ions and copper solid. That will be the favoured redox reaction. That's it for this episode of Bales Chemistry. I hope it's wrapped up the topic of electrochemical cells for you. If you've got any further questions, throw them in the comments below. And don't forget to hit the thumbs up if you liked watching this video.